Drew, though. Whoa. Okay, that was really creepy.
What? That's happened.
You're welcome.
That is creepy.
Why is it echoing?
I don't know. That better?
I think I heard Ozzy's ears.
I think that's better. Is that better, Jocelyn?
Yeah, I don't hear that weird echoing stuff anymore.
That was kind of crazy. Very strange. Okay. Drew, let's go.
Miss Danny.
I'm trying to get 1 second. I'm going to grab it nice because I'm hot. Lil, you coming? Come sit down. You're good. Come on. Oh, yeah. Thank you. What's up, Miss Jocelyn?
Guess what Hogwarts house I'm in?
What?
Hufflepuff.
I see it.
Yeah.
What's happening? What?
Her Hogwarts house is Hufflepuff.
How do you know your house? What your house is?
You can do, hey, Alex, hey, girls. You can do quizzes online, and it'll tell you.
Yeah.
Still got
I did 2 official Harry Potter quizzes.
I can
and
change
both-
the audio on that one over
I
there.
don't like the echoing.
Yeah, it's distracting. I don't know why it's doing that, but I'm gonna.
You can mute volume on one device because it's hearing echo.
All stuff.
On headphones, if you speak into a mic, it'll like say it out loud and the mic will pick it up again, so it'll sound like Ronaldo.
That should be better. Forget it's not good. All right, let's have a seat. Okey-dokey, folks. All right, I think we fixed it.
Did we?
Yeah, I think I pushed a button wrong on the iPad over there, the one that's filming the room, and it was like, come here, Oz. Hi. So anyway, to answer your question, Eleanor, you can go online and do quizzes to find out what your Hogwarts house is. Yeah.
It's Potter.
I did 2 of the quizzes and I got Hufflepuff both.
Okay, Jocelyn is a solid Hufflepuff. She got Hufflepuff both times. Yeah, you were what? Yeah, it was funny because the first time you did it, you were a Slytherin, and then the second time you did it, you were Hufflepuff.
I joked about that because I don't like Harry Potter.
No, you were.
No, I wasn't.
It was years ago. Maybe you just answered them all so that you would get
I got
Slytherin.
Hufflepuff first time, Slytherin second time, Hufflepuff
You're a
third
Hufflepuff.
time, and then I got Slytherin again.
You're clearly a Hufflepuff. Like, I don't know, you have a Slytherin, you have a bit of a Slytherin thing going. What do you think?
I mean to.
Lily, what do you think about Lily? I think you could do either, really.
Yeah, I'm like.
I'm solidly Hufflepuff. Do you know your house? Have you done it?
Just the one.
Hufflepuff. Have you girls done your house? No? Ah, gotta go on Potter. Oh, she's
I
got
have Harry's wand.
That's nice. Is that,
wand is it?
yeah, whose wand is it? Is it one of the regular ones or?
Harry Potter's.
That's Harry's wand.
I had the last time we had the Harry Potter party.
Mm-hmm.
I made the flying golden.
The
ball.
snitch?
Yeah.
You did? Yeah.
The snitch.
We have so much fun with Harry Potter Party, and I was seriously bummed out that it was a no-go this year, but I just couldn't foresee. And besides, I got that amazing letter from, the Minister of Magic and all. Did y'all see that amazing letter I got? Yeah. Hey, Scott. Yeah, we do.
Oh, Miss Danny.
Yeah.
Guess how many times I've watched the Harry Potter movies throughout COVID?
How many times has Jocelyn watched? I don't know, Jocelyn, how many?
Too many to count.
Too many to count. Yeah, I've lost count of them too.
That's
All right,
pretty much
so
what I watch.
Go
every
ahead
single
and
day.
start. I'm going to stick a thing in this with today's lesson. And I went ahead and did a slideshow. Now, I know Senya isn't going to make it today. She's kind of on a vacation that coincides with some dance competitions. I'll let her tell you what kind of dance it is because I'm going to get it wrong, but I think it's something like Irish dancing. No, I'm going to get it wrong. So, but anyway, she's been up to that the last couple of days. So she's been super busy. And Did anybody go anywhere for fall break? Anybody take a vacation, do anything fun? You went somewhere, you went to the beach, right?
Yeah.
Sky went to, was it Hilton Head? Yeah, did you go to the beach?
Yeah.
Yeah, fun? Cool, awesome.
I did actual school.
You did actual
I
school?
did.
Yeah, we did
We're home.
what we did
Bowling, I
partial school because we didn't have Spanish, we didn't have science, and we didn't have gymnastics because they're supposed to be putting in our air conditioning. All right, so let's look at page 88 if you have your book. If you don't, it's okay. And that's the beginning of lesson 3, chapter 3. And we started talking this week about metals, nonmetals, and metalloids. And so those of you that are, well, Jocelyn, can you see that I have a periodic table now up on the window? Yeah.
Yes.
And so if you're sitting over there, you kind of got to crane your neck. I tried putting it up here this morning, but it was too long and those little bases got in the way and you couldn't read it. So I need to find a good place for it. I thought maybe there was some way I could put it here, but it's going to make me crazy. So until I find where I want it to live, it's going to make me a little nuts, but it's big so we can all see it and can read it, which I like. So where on the periodic table do you find the metals primarily? Where? And then on the outsides, on the bottom, the top, the middle, like roughly where? In the middle, right out, like right in the middle. So can you guys tell me what are some characteristics that most metals have in common? Can you think? Yeah?
Shiny.
Shiny, that's a good one. It's luster. What else?
Malleable.
Malleable. Yeah, she's trying to come up with malleable. Malleable.
They're good conductors of electric current and heat.
Yeah, electric current and heat, good conductors. Do you guys know what malleable means? What's it
No. Wait, no, flexible. They're flexible and shapeable and moldable.
Yeah, like flexible. Drew said, like you can turn it into different things. You can hammer it, make it thin. Some metals are obviously more malleable than others. Like if you've worked with copper, you know copper is very malleable. You can bend it and shape it, right? And then there are some metals that are a lot harder to bend. And then of course we mix metals together to make alloys to make them even stronger. So we've got luster, meaning that they're shiny, right? They're good conductors and they tend to be somewhat bendable or malleable. So with conducting, as Jocelyn pointed out, it's both heat and what?
Electric current.
Electric current, right. And that actually has to do with the structure of the way the molecules are set up and the electron configuration that allows them to conduct current, because electricity is basically just like electrons shuffling along. So the fact that it can trade from molecule to molecule to molecule, make like a little train, that's how we get our conductivity. So you guys had some other properties of metals with these pictures here. So that first one was what? It's got some paper clips stuck to a rock. What does that tell you about it? A chunk of metal rock looking like thing with some paper clips stuck to it. What would make it stick?
It's magnetic.
Magnetic, right, Jocelyn? It's magnetic. So yeah, a lot of metals are magnetic. And we talked about malleable, and there's also ductile. Ductile means you can draw it out into a wire. You can stretch it to the point where it makes a wire, right? Gold is a great example. So yesterday I was at the dentist getting 3 fillings up here on my right, and it's terrible because my hygienist is like, your teeth are so clean and you do such a good job. You just have like bad bacteria in your mouth just how you are. It's nothing I can do, which stinks because like I'm fastidious about it and I still get cavities. It makes me want to cry. So anyway, the dentist told me after he put my fillings in, he put the composite ones, the ones that are white. But I have a bunch of the ones that look silver. Those are called amalgam. And that's like, it's a mixture of different metals. And I asked him, I said, do you ever just go through and take the amalgam ones out and replace them? Because over time, the amalgam ones, they're like a wedge in your tooth and they start to crack it. And they actually showed me pictures. They're like, your tooth's cracking here and here. And eventually these are going to come out. I'm like, ugh. And he started talking about filling options. Well, do you know that they used to fill teeth with gold? That was a thing. They would fill teeth with gold, or they'd put a gold tooth in your mouth to replace whatever tooth you lost.
From Home Alone.
Yeah, Home Alone, he had a gold tooth. You're right. Very good. So I asked him, I said, why gold? Because he said his favorite of all the filling options is gold. And I'm like, why? And he said, it's non-reactive with the human body. It's non-reactive with all of the bacteria that get in your mouth. It doesn't tarnish or anything like that. And he said, this was, I thought, the most interesting part. He said it wears down at the same rate as your tooth enamel, which is interesting because the amalgam, the silver ones, they don't wear down. Your teeth wear down faster, which causes you to have like this extra hard lump in your tooth, which is what makes it crack. And then the composite, the white stuff, wears down faster than your teeth. So the gold wears down perfect. So apparently way back in the day, they had it right. So that's your little interesting tidbit for gold in teeth. So let me, I'm gonna share my screen up here. I'll put this up. So I have some of our, this is basically just the pages from our book, from your homework in here. So we just talked about what properties are shared by most metals, right? They're shiny, malleable, ductile, solid at room temperature, good conductors of heat and electricity, right? We all agreed on that one. All right, so tell me about sodium and calcium. Look here. Find the sodium and the calcium.
Calcium's number 20, sodium's covering my left.
There you go. So calcium's number 20 and sodium is where? Do we see it?
14.
It's 11.
It's hard to see because you got
I know. It's right over Sky's head. Lovely Sky. You can be like Vanna White.
I
Would you
saw
like to?
silicon.
Yeah. Oh yeah, you saw silicon. Okay, so sodium and calcium are in different families of metals. Can somebody tell me what families they're in and what characteristics go with that family? This is color coded here, so it should help you out. What family is sodium in? Do you see?
So,
Yeah, you got it. Alkali metal. Yep. Okay. So remember, our families go up and down, and our periods go left and right. Okay. So it's in the alkali metal. Do you guys see that that's red at the bottom? It's true. Do you see at the bottom where it's red and it says alkali metal? So you got your sodium in there. And so what else is in there with it? What other metals? What do we see?
Lithium, potassium.
Lithium, potassium. That one's rubidium. Yep.
I just stopped because I was going to let someone else.
Cesium. And you see the last one is francium. All right. Yeah. And then can somebody tell me what's in the calcium family? What else is in there with calcium?
Barium. Well, I can't see.
Yeah. Beryllium.
Yes, and the magnesium that looks like calcium.
Yep. Strontium. That's the one that was bright red, remember?
Radium.
Barium and radium. Okay. There you go. All right. So what are some characteristics of that family that sodium is in? Did anybody write anything in their notes for number 2 for metals that would be helpful to answer this one?
it's not found uncombined in nature.
Very good. It's not found uncombined in nature. What does that tell you about it? What do you
It
guys
has to
think?
be mixed with something.
Mm-hmm. So that's because it is very reactive. And because it's very reactive, it has to do with the number of basically free spaces it has for electrons, right? It has a certain number of available spaces in its valence. And it's like, hey, everybody, I'm here. Let's party. Like all these guys on the left, y'all, these are the party animal people. That's who they are. These are the guys that can't be alone, right? They all want to hang with somebody at all times. They're always up for a party. They're always up for mixing with everybody. Whereas the dudes further over here, especially those guys in blue, those are the noble gases. Those are the major introverts that want to hang out at home. Like,
can we add hydrogen peroxide as an honorary member?
as an honorary member, mix them up.
That side's party animals.
There you go. Yeah, okay. So these guys are very, very reactive, right? They always want to be with somebody else, and they're always going to be found combined in nature. Now the calcium, oh, and they're also all these ones over here in the sodium, same family as sodium, they're soft, they're shiny. When we get one row over, they're fairly hard. Whoops, I missed a D there. They're fairly hard and they're silvery white. They're good conductors. They're less reactive, but they're still always found combined in nature. So you can't find, like, it's really hard to find pure calcium and pure sodium in nature. If you take pure sodium and toss it in water, if you were to get pure sodium, like you'd have to make it in a lab, right? Because you wouldn't find it that way in nature. Anybody know what it would do?
Someone tossing like a chunk of something, thing on a periodic table, and like was banging like a gunshot.
Oh yeah. Mm-hmm.
I forget what it was.
I think I forgot to put
tossing a pound of this into.
yeah, I forgot to put a thing of, I meant to put a clip of it in here, but we can still go find it.
Really big.
I think when Jason was at Virginia Tech, somebody took a chunk of it out of the lab and threw it in the duck pond, but
Oh my God.
it does a thing.
With the ducks?
Well, the ducks probably ran, flew away, but yeah.
That
So,
made a loud noise.
yeah. So how about the metal in group 13? Where do we find group 13? Are they more reactive or less reactive than group 1? So there we go. Yeah. Okay. So they're going to be less reactive because they're closer to the non-party animal side, right? The loners, these noble gases. You can think of the noble gases as being too noble and too snooty to hang out with anybody else. They're just too perfect. They don't need to hang. Their valence electrons are totally full. They don't need friends. They're very aloof, right? And then your reactivity in general is going to decrease as you go from the left to the right. And I'm going to show you a graphic in a minute that I'll put up there so you guys can see it, that has all these arrows on it that shows you trends in the table. So the lanthanides and the actinides, we see them at the bottom. Okay, so when you look at them, they're coming down in here.
The safe space you only go like LU or LR.
The what now?
I was confused with them for a minute, so I had to redo some because I wrote it wrong
Okay.
because of the 57 to 71.
Yeah, see how they stick out? They come out at the bottom, right?
Just a safe space.
So what period are they in? What periods are the lanthanides and the actinides? Do you guys know? Count them. 1, 2, 3, 4, 5. What period are they? They're 6 and 7. Do you see it? Count from the top. Count hydrogen. 1, lithium 2, potassium 3, rubidium 4, cesium. Oh wait, did I miss one? Yeah. I did. Sodium. Sorry. Hydrogen, lithium, sodium, potassium, rubidium. That's 1, 2, 3, 4, 5. Cesium is 6. Francium is 7. So in 6, if you go over to the third block, you'll see that purple block, that lavender one. That's your lanthanides and your actinides. And when you drop down, lanthanides are there, actinides are below it, and it goes all the way over. You see that?
Oh, you started.
Yeah.
This guy, Randall Monroe, he did a thing called What If?
Yeah.
It's like, people ask him weird questions, like, and he answers them. Like, what if you did a block of each element and made a periodic table? He's like, the first 4 rows would be fine. 5th row would kill you. The 6th row would burn you. 7th
Very
row,
true.
Go to the 7th row.
Very, very true.
Like, can you fly with machine guns and stuff? And then a how-to book.
A how-to book.
Yeah, it was really cool.
So why are they grouped at the bottom? Like, what is the point of pulling them out down there?
Well, it's usually in there to save space.
Yeah, that's exactly why. It makes the table more compact. If you were to organize them simply by characteristic, the way we do all of the other groups that go vertically, right, they would fall kind of right there below scandium, but it's really hard to envision how they would fit in there with everything else. So instead of making the table like super long with the big gap at the top for 3 rows, we just kind of pop those guys down out at the bottom. All right, so number 5 in your notes under metals, the reaction of metal with oxygen to form rust. What do we call that reaction? It's a really common reaction.
Corrosion.
Corrosion. Yeah, that's right. Corrosion. And it's actually a form of oxidation in this case, but yeah, corrosion. And so
Reacts to the oxygen reacts to the material after the wet.
right. Yeah. So what's the problem with that? What's the problem with having structures that corrode? Like what's the
weakens them very you can like break it in half.
right. So if you use iron, just straight up iron, it will start to rust with time, right? And then you'll lose your structure and everything else. So we typically find other ways to build things with other types of alloys, like steel.
Some kind of mixture that prevents rusting.
Yeah, those are alloys. So in alloys, when you mix like multiple kinds of metals together, like steel is an alloy, stainless steel is a type of steel. There's all kinds. Surgical steel, you've heard of that one? Heard of surgical steel? If you ever have a procedure done and they're using metal instruments on you, it's surgical steel. It's just a different grade of alloy that's less reactive with your body. So here's that vocabulary word again, a material that can be hammered into sheets. What's the word for that? Malleable, you got it. And here's another vocabulary again, the ability to transmit heat or electricity to other objects. What's that one? Conductivity, right. Okay, how about a material that can be drawn out into a wire? What do we call that? Ductile.
Ductile.
All day. All right, so the ease and speed with which an element combines with other substances. What's that one? Reactivity. Very good. Everybody have all those?
Yep.
All right, so when we start getting into things like our nonmetals and our metalloids. So the property of nonmetal is that it's the opposite of malleable and ductile. So what word do we use for that?
We have to use different letters for this.
Nah, in general, nonmetals and metalloids are going to be brittle, right? They're brittle. And then what happens to atoms of most nonmetals when they react with other elements? Do you guys know? This was in your notes too. This is on the nonmetal page.
They gain
Yeah, they usually gain electrons when they react. So what are some physical properties of nonmetals? Anybody got some? Physical properties of nonmetals. Physical properties. Remember what a physical property is?
They're more malleable.
No, they're not as malleable.
No.
That's right, yeah. No? You remember what physical properties are? Physical property means it's not going to change the substance, right? So how about are they shiny? No, they're not shiny, so they're dull. And they're not malleable, so they're brittle. And they're poor conductors. So now this is interesting. Metalloids. The metalloids are like this whole strip right here. See the kind of gold color? And it goes diagonally. Boron, silicon, germanium.
Isn't it a mixture technically?
No, these are all elements. Antimony, beryllium. Interestingly, like you've heard of arsenic before, right? Do you guys know what arsenic is? Well, what has been sort of the history of arsenic with humans? What? You know what?
It's like, it's really wrong.
Yeah, it's a poison. Yeah, it actually was used by some of the less moral people in the past to murder their foes. It's tasteless and colorless poison. And back not that long ago, it was the main ingredient in rat poison, which you could just go easily to the store and ask to purchase, and they would give you rat poison, and you would just go home and poison the rats and whoever else you intended to poison with your arsenic. So yeah, but interestingly, it was also used in dye, like a green dye that was very popular for wallpaper and stuff like that. So there is a point in history where people had toxic dye on their walls. There's a lot of toxic things. Do you guys remember reading about lead?
Oh yeah.
Yeah.
I've heard that there are people used to think that the tomatoes were poisonous.
Yeah.
But in reality, they just were using lead plates.
Yeah. So lead, what do you know about lead? Do you know?
Oh no, I was
Oh,
going
go ahead.
to say something. So you know from the Wizard of Oz, they didn't know for the witch's makeup they had dangerous smell, and one time she got her costume got trapped on the trapdoor, and now she has a giant scar because of the fire that went up because it was made.
I think the original actress for that part got so sick from the green paint. It wasn't arsenic. I think there was copper and something else in it. But got so sick from that green paint that she ended up resigning the role, which is how, what's her name? Margaret.
Margaret something.
Yeah, just slipped my mind. That's how she got it. I read that once. I don't know if that's true, but I read that once. So anyway, lead. They used to put lead in paint. They used to put lots of things in paint and wallpaper, but lead is extremely toxic and it causes neurological problems, especially if you consume it when your brain is still developing. So like if you're a child. So if you have a house that's over a certain age, when you sell it, you have to go through a process for whoever's buying it. Your real estate agent is always a part of this thing about lead paint. It's right there with any house you buy. But certainly if it's over a certain age, it's got lead paints in big letters, and you have to determine whether or not there might be lead paint in your house, because paint chips, like in this case, see how the paint chips off this? And
Yeah.
now, buy chippy paint, you know, whatever, but paint chips, and little kids will put those chips in their mouth when they crawl along and pick them up, and babies could get poisoned that way. And that was an issue.
Dogs could get poisoned like that too. Because
Yeah.
as puppies, they eat pretty much anything and everything.
Animals, yeah,
Like-
that's true.
Like
Anyway,
my grandma's puppy
years ago in-
Dixie. She eats rocks, sticks, and
Rocks
pretty
is
much
what
anything
puppies
that you
will
can get
eat.
into your mouth.
And yeah. So there was a couple years ago in a town in Michigan where their water had way high lead. I mean, it's not even way high compared to what used to be in paint, but now we allow so little for it to be legal, passable, certifiable clean water that it was out of range, and it's still an issue. It was a big issue for a while. So was there anything that anybody was stuck on or needed help with, or were you guys good for most of that so far? Just checking as we go. Good. Okay. So what are the nonmetals in group 16? So remember, families and, periods and groups. So 16, this is in your notes. What are the nonmetals in group 6?
Oxygen, sulfur, and selenium.
Yeah, selenium. Oxygen, sulfur, selenium. Yep. So here they go. There you go. Oxygen, sulfur, and selenium. And we know that they're nonmetals because if you look up here, it says diatomic nonmetal. What does diatomic mean? Does anybody want to guess?
No. Because I have no idea what it is.
Definitely a Latin creature.
Explain what
It
that
is a
means.
Latin prefix. So let me see if I look up the Latin prefix specifically and read it exactly as it's written. See if you guys can guess what it is. Okay, I'm going to give you exactly the way it reads. Okay. Di as a Latin prefix. English prefix would be bi. Derived from Latin, which is di, meaning two. Latin prefix is far more prevalent in common words, such as, let's see, bilingual, biceps, biped, and the more Greek di appears in diphthong and dilemma.
Does it have more than two, like, atoms or something?
Yeah, that's it.
Their, atomic?
Yeah, so that's the thing. So oxygen is never found by itself. It's always with another oxygen. If you want to talk about a party animal, it's a party animal, but it's a really like monogamous party animal. Like it is stuck with its one partner for life. Like it doesn't hang with any of the other. It does, but you always find it by itself. If you find it by itself.
If you have pure oxygen, you could get very, very sick.
Yeah, well, it is. You can have pure oxygen because it's a pure substance if you just have oxygen molecules, but you're never going to have an oxygen atom by himself. You're always going to have an oxygen with another oxygen because they are buddied up like that. And so anytime you're dealing with oxygen in a reaction, if you're dealing with the gas, you're always dealing with two atoms together to make a molecule. And that would be the same for the two below it, the sulfur and the selenium. So how do the chemical properties of halogens compare to noble gases? Where are the halogens? You guys see the halogens? Where are they? What color are the halogens? Do we see them? It doesn't say over here.
Green, the lighter green, no.
So the darker green, like and next
No,
to
the darker green, yeah, the darker green. NOFCLBRL, no.
You know what? Where are you reading? Oh, NCRBR. I'm trying to find where you're reading.
CL. It's 789 1735 53.
Ah, okay.
It's either that or the other greens.
Or the other greens. Okay. What do you guys think? Where do you find the halogens?
Both of them.
Is it on the one that you colored? Did the one that you colored have halogens in it?
Definitely.
Where are they?
Just the line down. Green F. So
Yeah.
117.
So they're right next to the noble gases. So this would be fluorine, chlorine, bromine, iodine, acetine, and what is the bottom? Oh, tennessine. Okay, named after Tennessee, obviously.
They're in the process of getting noble.
Yeah, they're in the process of getting noble. Okay, so here's the thing about halogens versus noble gases. All right, your halogen, if you think about it this way, you're, all right, going down in your periods, all your atoms have the same number of energy levels, right? And going across in your groups, you have the same number of valence electrons. So you remember what valence electrons are? Do you guys remember what they are? No, kind of? All right, so let me help you. I'll draw. Come here, puppy. I'm sorry, I have to move you. Yeah, he's like, I was asleep. So
Just make him just put
you're
the bed
gonna
down
have-
and make him sleep on there.
yeah, really, I should, because he's attached to me. Like, he truly is.
Yeah, if you just put me in there with the binary.
So you have your nucleus, okay, and you've got your positives and then your no charges in here, right? All right, and then you have all your shells, right? If we just do this like a Bohr model, okay, the outermost shell, this is your valence shell. And however many of these you have, however many electrons you have, are your valence electrons, and they matter because they're the ones that are going to interact with other things. Nothing in here is typically going to do much until these guys go first, because they're sitting there on the outside with their negative charge, wanting buddies. So look at the top one there, fluorine. All right. Let's look at fluorine. What's the number for fluorine?
9.
Fluorine is 9. Okay. So then how many protons do I have?
A couple.
If it's 9,
Because that's 2.
if it's 9, how many protons do I have?
Proteins, yes.
Protons, yeah. So I have 9, right. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these dudes. Neutrons.
Zero
right.
proteins.
Now, do you guys know, let's see, more of the other group, but when we get into, where's the best example of it? Remember we talked about how energy shells have a certain number of electrons per, I'll find it in here for you. It's easier, I want you guys to look at it. So each shell has a certain number of electrons that can be allowed in the shell, right? And it's kind of like, it's a pattern. Here we go. Here we go.
Create atomic bombs by just shoving them in.
Let's see? Okay. All right, you look at this for me, Sky. See right here? See where it says 1s? That's your first energy level, and your second energy level, N1, N2. So, maybe that's not the easiest one for you to read. What's the easiest one to read? I don't want to just tell you. I want you to do them. Number of orbitals, yeah, blah, 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 blah. Where's the best example? The energy one. Hold on a second. I'm trying to find the best one for you guys to look at, but I don't know. Okay, well, this is an example of how it starts. This first one is, what's it say? It says 1s. Do you see where it says 1s2? Okay, so this means this is your first energy level, and it has 2 of these guys. 1, 2. Okay, now what's the next thing say? Let's say like 2s. 2s, there should be a number behind it. And there's 2s2. See that? Okay, 2s2. S1s are the spherical shape. So it's going to have 2 as well. So now how many electrons do I have so far? How many do I have so far? 1, 2, 3, 4. Right? How many are we trying to get to?
10.
Okay, what's the next one? 1s2, 2s2. 2p2. Okay, so you have a 2p2, and then you have a, no, it's a 2p6. There it is. Okay, so 2p6. So the next one isn't as round. It's sort of, move him over. It's sort of a weird shape. It sort of goes like this, for lack of a better way. All right, kind of dumbbell shaped. And how many go on there? 6, right? Okay. So how many more do I need to get to 9? I have 4. I need 5.
5.
6 here. So if we put on the 5 we need, 1, 2,
It looks like
3, 4, 5. I can hold 1 more, but I don't have it, right? I don't have 1 more, but I could hold 1 more. If you were a noble gas, if this were neon, which is 10, that would be full. And that's why he doesn't party with anybody else. Because he's full. Hang on. He's full. He doesn't have room for anybody else in his life. But if you are fluorine, if you are fluorine, you have this one empty little hole in your heart, basically, and you've got to find somebody to fill it because this is super negative, and you need to balance out the positive, negative deal, and this explosion. Hey, here I am. I've got one spot. That makes these super, super reactive, okay? Because this right here. If you were to back up and go from fluorine to oxygen, you're gonna take away another one of these, right? So here's where it's all math. If you are an atom, let's say, look at what's a good one? Look at hydrogen, okay? Hydrogen has how many electrons?
One.
One electron, okay? And it's got this little one guy here, right? And then oxygen has how many electrons?
8.
8. So let's just pretend we're looking at the valence only, okay? 4, 5, 6, 7, 8. Okay, now the valence isn't going to have 8. It's going to have how many? We built up this one, okay? So we built up this one towards 9. So it would basically, your valence would be missing 2. So it would have 1, 2, 3, 4, 5, 6. So it's these 6 that are going to matter, okay? Because the ones inside don't matter, just the outside ones, okay? These 6 are going to matter. Are you watching, Drew?
I have a question.
Yeah, hang on. These 6 are going to matter. And how many more can it take? You remember? It can take 8. What can take 1, 2, 3, 4, where are we? 1, 2, 3, 4, 5, 6. But it's missing these 2, and it has 1, 2, 3, 4. So now we're down here. I missed 1, sorry, that was my fault. Okay, it's got 4. It has room for 2 more, right? That makes sense? How about now? It has 4. It has room for 2 more. Hydrogen has 1. What's the formula for water?
H2O.
How many hydrogens can fit with this one oxygen?
2.
2. Ella's got it. Look. This one, and then 1 more. So what you end up with is you have this oxygen here, and we can fit 6 in that valence, but it's only got 4 in there. So 1, 2, 3, 4, and it's got 2 spaces that are empty. But look, here's a hydrogen. This is the oxygen. This is the hydrogen. He has 1. There's another hydrogen. He has 1. So now it's full. That's all it is. They click. It's almost like Legos. How many empty nubbies do you have for holes? All right. So for B, for this one, how do you compare? Come on. Come on. Hey, over here.
He wants to be picked up.
He does. How do you compare noble gases to the halogens? The halogens are super reactive and noble gases are non-reactive. They don't have any space in their life for anyone else, right?
The introverts and the extroverts.
Yeah. So how is the periodic table organized? All right. So
Ozzy looked
By
like he was
react-
3.
Reactivity and atomic number.
Right. So you've got a periodic table organized by increasing atomic number. Elements are arranged into rows that are called periods, columns that are called groups, sometimes they're called families. And the elements in the same group have similar properties. All right, so here's what I want to show you. If you look up there, you guys that are here, if you look up there, Drew, look behind you. So if you look at the periodic table, the lavender line says electron affinity. And then the blue line says ionization energy. Okay, one of those is about giving up electrons and the other one is about taking electrons. But we haven't gotten there yet. But if you notice, the electron affinity is going to go from left to right and bottom to top. And the ionization energy does the same thing, left to right, bottom to top. The pink one says atomic radius. And that's like, you know what a radius is? It's like from a circle, from the center of the circle to the outside. So it's basically how big the atom is. And if you notice, they get smaller going down and then they get larger going down and then they get larger going right to left. And there are reasons for that too, but that gets kind of crazy. And then your metallic characteristics are going one way. That's the silver one or the gray one. And your non-metallic characteristics are going the other way. So if you look at the table, it's not, oh, and electronegativity too, that's another one. That's like how negative the charge is. And if you look, like the most reactive ones, with the exception of those exception of the noble gases there, are in that corner where the fluorine was, right? Headed towards that corner. And if you look at the table then, so it's not just atomic number, and it's all these other characteristics too. And the pattern repeats again and again. So I wanted to tell you a little bit about cyclotrons and synchrotrons. I think your book mentioned just a little of it, but it's about making elements basically. So if we're gonna make some super heavy elements, those are the ones called synthetic, okay? And these are the ones that are man-made. So some of these ones at the very, very bottom, we can make ourselves, but the way they make them is they use usually it's a synchrotron for making them. So you put the particles in it, they accelerate them very, very fast. You ever heard of a particle collider? That's what it is. Causes the particles to collide enough to the point where their mass combines and you get a new element. But you usually only get the new element for a minute or a couple seconds because, yeah, you can't keep it going.
1 millisecond later for some, like,
yeah,
1,000 atoms.
that's true. So so what they do is they spin them. And the cyclotrons, I put this picture up there because the cyclotrons are very often used now for proton therapy, which is used in often brain cancer treatment. So it says the protons enable larger doses of radiation to be used to treat cancers while significantly reducing damage to healthy tissue, as opposed to X-ray, which is what they used to do. So this is a newer thing, but you can find a cyclotron in pretty much any hospital, okay? You can fit a cyclotron in a room, and it's a particle accelerator, but it's not the kind they use to make new elements. The synchrotron, this is how many synchrotrons there are. This is your world map of synchrotrons. Nowhere near as many as the cyclotrons, nowhere near as many. Synchrotrons are massive, and when I say massive, I mean huge, like multiple blocks. They're typically underground, but they're not all underground, and they're like a giant donut. And when they accelerate the particles through them, they accelerate them through this huge loop. And there's a very famous one in France called CERN, and that one was one of the earlier ones. I'll show you real quick that I can find you a picture of CERN. Well, the problem is that they're very, they can be very dangerous if they're not well managed. So here are some images of CERN to give you an idea. CERN is in Orly, I believe, France, but like this is what the inside of the thing looks like. Holy moly. There's your tube, okay? They accelerate the particles through. Y'all see that up there? But from above ground, where's a good one from above ground?
Cool. They look like one of those.
Oh, they do look cool. Like, look at this one. Do you see the line? The line is where the accelerator exists underground, or where they want to build it underground. Like, that's how big it is. They want to build it under, you see how big that is? That is huge, guys. And if you look them up, I'm typing one-handed because I'm holding a dog. This is how most of them look. So this is an example right here, just like a schematic of one. You can see that circle, that's where the accelerating goes on. But here's some aerial photos of actual synchrotrons, and you can see how big they are. These are not little by any means. Huge, huge, huge. Like, look at that one. Big things, right? Yeah, Hot Wheel track. Yeah, it's like a massive Hot Wheel track. This one's cool. Ooh. And this one looks fancy. Look at that. Like, they made it look fancy. That's the schematic for it, but there's pictures of it too. And then the other thing I wanted to show you real fast, sodium. Pure sodium in water. I have no idea what's going to pull up here, so let's see. Pure sodium in pond. Oh, somebody did it. Somebody's always doing it. Here we go. I haven't watched this, so I'm hoping there's not language in it, as I meant to get one earlier that I knew was safe. So here we go. Oh, we gotta have an ad. Can't be a thing without an ad.
I have this thing where I can speed up YouTube up to 16 times faster, and it works on ads too. So
Yeah, you see this dude?
so I programmed something.
Maybe, if it'll load.
I do not see the dude.
Oh, here we go. He's got some pure sodium, like from a lab. You watching up there, guys?
I cannot see the dude.
You can't see the dude? Okay, hold on, wait.
Just saying, you're probably lying.
Hang on 1 second, 1 second. It wants to look here. Okay, now you see him? You see him now, Jocelyn?
No, I,
Yeah.
yeah, now I do.
Okay, watch him. You watching? He's got pure sodium. Remember I told you it's super reactive.
Chuck it.
Chuck it in the pond.
But they're gonna also be loud bangs.
I don't know why they're not making sound, but
Probably might be a TV.
yeah, could be anything.
Wait.
You'll get the point anyway.
Probably.
Someone going in the water while they're doing it?
No, I wouldn't want to be.
Heck no.
Here we go.
Dad, these is my.
What about the fishies? Wait, what?
Right, right?
Now it looks like a fast.
Isn't that cool? I love it. That's fun.
I recently also saw a video where there was this microwave, you know those big like round satellite dishes? Well, they look like drums.
Yeah.
Yeah, and it's like you microwave some.
It like lit on
And there was
fire,
like a
but on
on
water.
more than 200 pounds worth of acorns
Oh,
in it, and they took they had a.
That was ironic. Having the water catch on
all right, well,
fire.
I gotta let Jocelyn go because it's 10:47 and we need to start lab. So, so for anybody that's at home today, it's pretty easy to run this lab yourself. If you want to run it with somebody to help you think, go ahead because it is kind of this is a code breaker lab. This is a mental exercise puzzle lab. But the idea is you're gonna take. Hang on a sec. Yeah. The idea is you're gonna take this concept of trends in the periodic table and apply it to some mystery elements the way Mendeleev did to set up his table. So it should be cool. So y'all tell Jocelyn later.
Bye, Jocelyn.
All right, we'll see you later.
Goodbye.
Bye. Yep, that's the lab.
How many
So
pages are